Hello, my dear friends. In our last class, we have discussed three derivations: conservation of mass, momentum, and energy. Conservation of mass or continuity equation states that m dot or rho AC, the mass flow rate, is a constant. Then we have derived the momentum equation or conservation of momentum. We have started the derivation from the statement of Newton's second law of motion. And finally, we have derived the conservation of energy. And we have obtained H01 is equal to H02, or in other words, the stagnation enthalpy remains a constant. Today, let us start our discussion with the topic effect of Mach number on compressibility. I have told before, fluids can be classified into two: incompressible fluids and compressible fluids. Incompressible fluids are those fluids whose density remain a constant during its course of flow. Example, liquids. Now coming to compressible fluids, all the gases can be called compressible fluids as there is a change in its density during its course of flow. But we have to understand that the velocity or Mach number plays an important role in compressibility. Only if the Mach number is greater than 0.3, there is a remarkable change in its density. So let us see how this Mach number affects compressibility. According to Bernoulli's principle, which we have well defined in your mechanics of fluids, the sum of pressure energy, kinetic energy, and potential energy is a constant. Consider a convergent divergent nozzle like this. The entry is marked as section 1 and the throat is marked as section 2. The properties at the entry, pressure and velocity, are P1 and C1 respectively. And that at throat, they are P2 and C2. The pressure and velocity at the throat are given by P2 and C2. Then, according to Bernoulli's principle, for an incompressible flow, that is, for fluids whose density remain a constant, P1 plus rho C1 square plus rho GZ1 is equal to P2 plus half rho C2 square plus rho GZ2. That is, the sum of pressure energy, kinetic energy per unit volume, and potential energy per unit volume is a constant. Or in other words, P plus half rho C square plus rho GZ is a constant. Here we are not indicating as rho 1 and rho 2 because this is the case for an incompressible fluid, so the density remains a constant. For gases, we know we don't have to consider the altitude, and therefore Z is equal to 0. And hence the third term, the potential energy term, can be easily neglected. Therefore, we will be obtaining P plus half rho C square is a constant. This constant obtained is the stagnation pressure, as the stagnation pressure is obtained by isentropically decelerating the flow to zero velocity at zero altitude. Hence, the constant can be renamed as P0 or the stagnation pressure. The increase in this pressure, which is caused by the deceleration of the fluid velocity, is called dynamic pressure. So this term, dynamic pressure, which is indicated by Q, is very important. So Q, dynamic pressure, is defined as the increase in pressure caused by the deceleration of fluid velocity, or in simple terms, Q is equal to P0 minus P. For an incompressible flow, the dynamic pressure Qin stands for incompressible flow, is equal to P0 minus P, which is earlier obtained as half rho C square. Now let us discuss the case for a compressible flow. For a compressible flow, we know the relation between pressure and stagnation pressure. P0 by P is equal to 1 plus gamma minus 1 by 2 m square all raised to gamma by gamma minus 1. Now let us compute the value of dynamic pressure Q for compressible flow. QCO or Q for compressible flow is equal to P0 minus P, that's okay, which is equal to, we are taking the P term outside the bracket, so P into P0 by P minus 1. We have already obtained an expression for P0 by P. Let us substitute that expression in this equation. And we have to simplify this expression. This can be easily done using the Taylor series expansion, which we have already studied in engineering mathematics. 1 plus x all raised to n. The expansion of this can be used to compute the value of QCO. In this general series of expansion, x is equal to, for our case, x is equal to gamma minus 1 by 2 m square. And the exponent n is equal to gamma by gamma minus 1. So our expression QCO can be simplified using this series of expansion. And we will be obtaining as this. So this is the expression for P0. Now let us simplify this expression. There are many terms which are having gamma minus 1 as common. So let us remove the gamma minus 1 terms. Let us cancel those terms. And we will be obtaining like this. And in the next step, we are taking the term gamma m square by 2 outside the bracket. So this is our new expression. So this is the current expression for QCO, or dynamic pressure for a compressible flow. For a perfect gas, we know gamma P m square, that is the term outside the bracket, is equal to gamma P C square by A square, because C square by A square is nothing but our Mach number square, which is equal to gamma P C square by gamma RT, because A square, the square of velocity of sound, is equal to gamma RT. And in the next step, we are cancelling the gamma term in numerator and denominator. And finally, we will be obtaining P by RT into C square. But we know P by RT is nothing but density. So that is equal to rho C square. Now let us substitute that back to our original equation for Q0. And for an incompressible flow, the dynamic pressure Q0 is given as rho C square by 2 into 1 plus m square by 4 plus 2 minus gamma by 24 m raised to 4 plus etc. So this is the expression for dynamic pressure Q0 for an incompressible flow. If you examine this expression, you know that dynamic pressure Q0 is only dependent on the Mach number, provided we have a constant gamma. As there is an increase in Mach number, the compressibility increases. So that is how we define the effect of Mach number on compressibility. Next, let us define the term pressure coefficient, or Cp. In problems involving the flow of compressible flow over solid bodies like an aerofoil, a non-dimensional coefficient called pressure coefficient, or Cp, is employed to represent the performance. You have to consider a compressible fluid flowing over a solid body. Let rho delta be the density of the medium and C delta be the corresponding velocity. Then the pressure coefficient Cp is equal to P0, stagnation pressure, minus P delta, the static pressure, divided by Q. For an incompressible flow, that value is of course unity, because we know the dynamic pressure Q is equal to P0 minus P. Now, coming to the case of a compressible flow, pressure coefficient Cp is equal to P0 minus P delta divided by half rho delta by C delta square. The numerator P0 by P delta is nothing but QCO, which is also known as the dynamic pressure for a compressible flow. And we have already defined an equation for QCO. It is given like this. Now let us substitute this expression for the expression of Cp. And hence Cp is equal to 1 plus m square by 4 plus 2 minus gamma by 24 into m raised to 4 plus etc. And this expression will give you the percentage deviation of the pressure coefficient for an incompressible flow from a compressible flow. And as I told before, the only variable here is the Mach number. So as the Mach number increases, the pressure coefficient, the deviation of pressure also increases considerably. I have just shown a graph to illustrate the percentage deviation of the pressure for different Mach numbers from 0.1 to 1.0. As we know, for lower Mach numbers like 0.1, 0.2, 0.3, etc., the percentage deviation of pressure is negligibly small. But as the Mach number increases, when it is 1, you can see the percentage deviation is much higher, and it is equal to 27.5%. Next, let us discuss yet another important thing, that is known as impulse function. Impulse function is defined as the sum of pressure force term and the momentum term for any section of flow. Impulse function is indicated by F, and it is equal to PA, the pressure force term, plus rho AC square, the momentum term. Now, we can make some rearrangement. Instead of rho, I am going to write P by RT into AC square, which is equal to PA. I am multiplying numerator and denominator with gamma. So PA plus gamma P by gamma RT into AC square, which is equal to PA plus, the denominator of the second term, that is nothing but the square of velocity of sound A square. So the expression can be rewritten as PA plus gamma PA into C square by A square, and we know C square by A square is nothing but Mach number square, M square. And finally, the impulse function F is equal to PA into 1 plus gamma M square. So that is a very important expression for impulse function, which is used for solving many problems. We know this compressible fluid will be flowing through some ducts or nozzles or diffusers. The net force acting on the fluid by the internal walls of these ducts, diffusers or nozzles, or by any obstructions in the flow can be computed using this expression. F net is equal to F2 minus F1, where F2 and F1 are the impulse functions at two different sections. So this can be the expressions for F2 and F1 has been introduced here. This is another form of F2 and F1 which we have seen in the previous slide. So the F net, it is the thrust produced by the stream due to the flow between two sections 1 and 2, and it is also known as stream thrust. And with this, we have come to the end of today's session. I hope all of you have enjoyed the session. Thank you.